7.11 practice problems. The equilibrium constants for the dissolution, KSP, of various substances in aqueous solutions at 25 degrees Celsius are listed in the table above. Which of the following provides a correct comparison of the molar solubilities, S, of some of the substances based on their KSP? So, very important to make sure that we are matching the equations given here. So, A says that the solubilities for copper 1 cyanide and nickel 2 carbonate are calculated using S is equal to the square root of KSP, and that the nickel 2 carbonate has a lower molar solubility than the copper 1 cyanide. So looking between here, these two, they are both KSP is equal to the S squared, so the square root of KSP is useful for both of them. And then we just need to go ahead and check to see if the nickel 2 carbonate has a lower molar solubility than the copper 1 cyanide. So I'll go ahead and put those in. So the KSP of the copper 1 cyanide is calculated as the square root of 3.47 E negative 20. Okay, and then that's for the copper. And then for the nickel, we will have the square root and so it says that the nickel has a lower solubility than the copper 2 cyanide, or copper 1 cyanide, and that is not true. The copper 1 cyanide has a greater solubility, or a smaller solubility than the nickel. So the inverse statement we have with B is going to be correct. So we can go ahead and say that it's definitely B, as it's the same statement, just says that the copper has a lower molar solubility than the nickel, which we did find out to be true. We can also disprove C and D pretty easily. As you can see, they are raised to the third, and this is a traditional square root, not a cube root, and so we could eliminate C and D pretty easily as well. The chemical equation above represents the equilibrium that coexists in a saturated solution of silver carbonate. If S represents the molar solubility of silver carbonate, which of the following mathematical expressions shows how to calculate S based off of KSP? So, as a reminder, the KSP is going to be calculated based off of just the concentrations of anything that is aqueous, and so just the silver and the carbonate, and then we have our coefficient of silver being 2, so we have that squared, and then carbonate where we have the coefficient being 1, so we're just leaving that alone. So if we were, for every 1 silver carbonate that dissolves, we have 2 silvers that are produced, and then 1 carbonate. Which can be substituted as S. This is still squared, and that is equal to the KSP. then you go ahead and multiply these out. So this is going to be 2 squared, which is 4 s squared times s. So s cubed is equal to KSP. And then we'd go ahead and solve for s. So we'll divide both sides by 4. And we'll be left with s cubed is equal to the KSP divided by 4. And then we need to do a cube root to solve for s. And so we should be left with s is equal to the cube root of KSP divided by 4. And that matches option D. According to the information about the dissolution of barium iodate shown above, the correct value for S, the molar solubility for barium iodate, can be calculated using the following mathematical relationships. So we know that it's just going to be that the KSP is equal to the concentration of the barium raised to nothing, since we don't have a coefficient there, and the iodate squared. Then substitute in for S, so 1 barium, so 1 S for every, and then 2 S for every iodate squared. And so we are left with that the KSP is going to be equal to 2 squared is 4, and so we end up with 4s cubed is equal to the KSP. And reminder that the KSP was given here as 4 times 10 to the negative 9th molar, and so just substituting that in equals 4s cubed is option choice D. What is the molar solubility in water for silver chromate? And the KSP for silver chromate is 8 times 10 to the negative 12th. And so they don't provide the equation, so we are going to have to write that ourselves. So the silver chromate will dissociate into 2 silvers and a single chromate. And so that means that the KSP is equal to the concentration of silver squared times the concentration of the chromate. Substituting in for S, we have 2s squared S, so that leaves us with 2 squared is 4s cubed is equal to the KSP, and then I need to solve for S, so I will divide both sides by 4 and then cube root, and since I have 8 times 10 to the negative 12th, so 8e negative 12 divided by 4, and then the cube root of that. So we can obviously eliminate the one where we don't have anything happening to the KSP there. And then also I can eliminate the one that is just a square root. This is just the 8 divided by 4, no cube root. 8 divided by 4 should give me 2 and then cube root there. So I'm going to select E as my answer choice. Based on the KSP values for the table opposite, a saturated solution of which of the following compounds has the highest concentration of chloride? So highest concentration of chloride, we're looking for the KSP to be relatively large. It means that we are going to have a lot of the chloride dissociating. I can see that the mercury chloride complex, the KSP is the smallest. So even though I do have Cl2 there, my KSP is very, very small. So that's going to go ahead and be eliminated. Then looking between these three, I can see that the largest KSP is also the one where I am left with Cl2, which does mean that I am going to have twice the Cl's, twice the number of chlorides that are present, and my KSP is the largest. So A, by and large, is the runaway best choice for that answer. If you were left with something where you had the KSP of one of these where we have just a single chloride slightly larger than that of the compound that has 2 chlorines, remember that again, we are dealing with 2 chlorines for every one here, and the KSP is already accounting for that. Calcium hydroxide precipitates when 1 gram of calcium carbide is added to 1 liter of distilled water at room temperature. If 0.064 grams of the calcium carbide with a molar mass of 64 grams per mole is used instead, and all of it reacts, which of the following will occur and why? And then we have that the statement of that the KSP for the calcium hydroxide is 8 times 10 to the negative 8th. Okay, so we see that we have decreased our amount of the calcium carbide. We went from, we decreased it to 0.064 grams. So we do need to go ahead and convert all of these to moles, and we have the molar mass of the calcium carbide. So the 0.064 divided by the 64 that was given gives us 0.001 moles of the calcium carbide. And then I can see that for every 1 mole of the calcium carbide, there is 1 mole of the calcium hydroxide. And so that means that I'm going to produce also this many moles of the calcium hydroxide. And then I can go ahead and calculate Q. I know that this is per 1 liter, so this is per 1 liter. Okay, so then I can go ahead and calculate for Q. So Q is going to be equal to my concentration of my calcium, which I have 1 calcium, and then my hydroxide squared, since I have 2 hydroxides per every calcium hydroxide. And so the concentration of calcium is just 1 of this, so 0.001, and then times the hydroxide amount is twice that of the calcium hydroxide, since there are 2 hydroxides per calcium hydroxide. So 0.001 times 2, and that number squared. So 0.001 times 0.001 times 2. Let me just go ahead and 0.001 times 0.002, that's just going to be that squared, gives me that, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so 4e negative 9. Okay, which is smaller than the KSP, which means that I can eliminate anything that says that the Q is going to be larger, because we do know that Q is smaller than the KSP. And since the Q is smaller than the KSP, that means that we are not saturated. So option D states that the calcium hydroxide will not precipitate because my Q is smaller than KSP, meaning I am unsaturated. The value of KSP for lead 2 chloride is 1.6 times 10 to the negative 5th. What is the lowest concentration of chloride ions that would be needed to begin the precipitation of lead 2 chloride in a 0.01 molar solution of lead 2 nitrate? The value for KSP for the lead 2 chloride is 1.6 times 10 to the negative fifth. We're looking for the lowest concentration of chlorine that would needed to be to precipitate the lead 2 chloride if we already have 0.01 molar of the lead 2 nitrate present. So we can go ahead and set this as the KSP is equal to the concentration of the lead 2 nitrate that we already have, and then the chloride squared, since we have 2 chlorines present there, which means that when it dissociates, we have a coefficient of 2, so we're going to square it. So 1.6 e negative 5 is equal to the concentration of my lead, which is 0.01, and then multiply that by my concentration of chloride squared. I'll divide both sides by the 0.01, so 1.6 times 10 to the negative fifth divided by 0.01 gives me 0.0016, and that's equal to the concentration of chloride squared. And so I just need to square root both sides. And so the square root of this number gives me 0.04, otherwise known as 4 times 10 to the 12 negative second. And that would be answer choice E. In a saturated solution of zinc hydroxide at 25 degrees Celsius, the value for the concentration of hydroxide is 2 times 10 to the negative 6 molar. What is the value of the solubility product constant KSP at 25 degrees Celsius? So that we know that our overall KSP is going to be equal to the concentration of the zinc multiplied by our concentration for the hydroxide squared. We have the value for the hydroxide, which, remember, since this dissociates and we get 2 hydroxides for every 1 zinc, this is the concentration of zinc, but times 2. So divided by 2 gives me the concentration of zinc. So 1, since 2 divided by 2 is 1. So 1e negative 6 times 2e negative 6 squared. So 1e negative 6 times 2e negative 6 squared gets me 4 times 10 to the negative 18th for my KSP, which is answer choice A. A 1 liter solution of silver nitrate and lead 2 nitrate has a silver ion concentration of 0.2 molar and a lead 2 concentration of 0.001 molar. A 0.001 molar sample of potassium sulfate is added to the solution. Based off of the information in the table above, which of the following occur? And we're going to assume that the volume concentration in the solution is negligible, which means that we're going to be dealing with just straight molar for the concentration of sulfate. So Q for silver is going to be equal to the concentration of silver that I have, which is 0.02, and that's going to be squared because I get 2 silvers for every 1 sulfate, and then multiplied by the concentration of the sulfate. We have 1 for every potassium sulfate, and this is per 1 liter already, so 0.001 which is 4e negative 7. And then for my lead Q, we're going to do basically the same thing. So the concentration of the lead that I have here is 0.001, and then we just have one lead for every sulfate, so no squaring going on. And then again, just one sulfate, and there was only one sulfate here, so as well. Gets me a Q of 1e negative 6. Now I will compare my Qs to the KSPs stated. So the KSP for the silver is 1 times 10 to the negative 5th, which is a larger number than the Q, which means that silver is not going to precipitate. So I'm going to eliminate anything that says that the silver will precipitate. And then I will compare my lead Q and KSP. So the lead Q is 1 times 10 to the negative 6th, which is a larger number than 1 times 10 to the negative 8th. So that means that the lead will precipitate. So option C